Hello, good morning and good afternoon, and welcome to this third session on the Cisco Quantum Nuggets. My name is Giuseppe Cinque. I'm Principal Architect for Cisco Networking Academy, and I curate this series of quantum science and technology. Next slides, please. So I want to remind that you can find the previous sessions both on YouTube, or if you are a Cisco Networking Academy instructor, also on netacad.com, where you can also find additional resource like the slide deck. Next slide, please. So quantum science and technology is really this amazing field that uses the properties of atomic particle, very strange and unintuitive property like superposition, entanglement, to fundamentally transform how we compute, how we communicate, and how we sense the world around us. And today's topic could not be more timely. In fact, in the past few months, we have seen the most important honor, like the Nobel Prize, but also like the Turing Award, be assigned to scientists that have done research in this field. So this is really the time to dive in this technology and provide all our students with the right literacy. And today, the topic of today is a very important one, is what is Cisco doing in this field? What is Cisco doing in quantum? And to tackle that, we have a very welcome and estimate guest, Tim Singetti. He is responsible for the Cisco Quantum Ready services, but not only being an incredible technical leader, is an incredible speaker and presenter, able to transform very mind-blowing concept in very easy to digest. So without further ado, I give the floor to you, Tim.
Thank you, Giuseppe. Very kind introduction. I'm a big fan. I love the work Giuseppe's been doing and his previous session. If you haven't checked it out, by all means do so. And it's a pleasure and honor to be part of this educational track then, and I'm just very happy. So the overall goal of this session is to showcase what we're doing in quantum, and I can show you that what we're doing in just one slide. In fact, why don't I do that? What are we doing? Well, perhaps you caught our latest announcement. This went out just a few weeks ago. We built the world's first universal quantum switch. And so some key elements of this switch is it's multimodal, it's high fidelity, entanglement, teleportation, and entanglement switching. I can throw all that at you, but does it mean anything? What does it all gather to and amount to? Well, I think then to truly appreciate this and to understand what we're doing, we kind of have to take a little bit of a step back and set some fundamentals. I know you already have some of these, but just in case you don't, or to reinforce some fundamentals so that these terminologies will make sense, and also aspects of this achievement, like why is it so impressive that we were able to use real-world infrastructure and low energy and operate at room temperature. You saw the image just a moment ago that Giuseppe was sharing about a quantum computer. That's super cool, that minus 272 degrees Celsius, and you saw all the nitrogen requirements to keep it there. How did we achieve these engineering feats? Well, in order for that to make sense, like I say, we have to kind of go back. There's a dependency. To understand this switch, we have to understand quantum networking. To understand that, we have to understand teleporting. Is it real? How does it actually work? To understand that, you have to understand entanglement and then basics of mechanics. So let's peel back that onion. Let's try and build layer by layer. The goal of this session is then to leave you with, again, reinforced or new quantum literacy, enough fundamental concepts to understand what's going on in the field specifically of quantum networking, and then also to showcase the breakthroughs that we're leading in this field. Does that make sense? Okay, so what I invite you to do is to look for these key points. I'm going to throw a lot of information, and I don't expect it all to be absorbed. At least when I go through these type of sessions and webinars and papers, I often have to read them and reread them and reread them. And that's not uncommon. It's a complex field. It's very, as Giuseppe mentioned, it's at times very counterintuitive, even paradoxical. It's difficult to wrap our heads around it, even for the Nobel laureates. There's some fundamentals in quantum that just don't make sense. And yet they're observed, they're predicted, we can leverage them. So anyways, let's look for these points. If you take away these 5 points, I think it'll be a good use of time. So I always like to start with why. So let's establish the use cases of why even build quantum networks. Then let's look at some of the key properties of quantum bits, particularly as they relate to networking. And we're going to look for 3 of those. Here's an interesting question. And you almost see a lot of hype in the media, a lot of exaggeration, and it's important then to be able to distill fact from fiction and myth from FUD. So sometimes when you come across articles talking about quantum teleportation, they almost always like to say, hey, you can transport information faster than light. Is that really the case? We're going to examine that, and we're going to give a very thorough explanation of whether it is or isn't. Will quantum networks replace classical networks? These are coming. These will play a very big role in our future, but to what degree will they do completely retrofit, or what's going to happen? And finally, what's Cisco doing in this space? Okay, let's look for those points as we go. So again, I love starting with why. Simon Sinek, I think, got this completely right. Before you get into the how, the details, the mechanics, the designs, why? Why even do any of this? Well, let's look at the use cases for building quantum network. The original use case for quantum networks was for cryptography, for keeping things secure, particularly key exchanges. So the first principal use of a quantum network was quantum key distribution, recognizing that quantum has a unique property, which we're going to talk about, specifically no cloning. And as such, it's impossible to copy information that's encapsulated in a quantum state. If you do try and copy it, the receivers, senders and receivers, can immediately tell if there's any eavesdropping, and therefore that information is invalid. And so you could use these properties to exchange keys that in a mathematically secure way, provided that the access to the networks, the quantum key distribution networks, and everything else is also done in a secure manner. The actual exchange, mathematically proven secure. Well, that was one use case, but the more emerging use case, the bigger use case, the prime use case going forward is this: distributed quantum computing. So recognizing that quantum computers, what they're good at, they're not good at everything. Giuseppe covered this with you. You could use a quantum computer to do word processing, but it's not going to gain you anything. Any logical circuit, any Boolean circuit on a regular digital computer, you could replicate on a quantum machine, but it doesn't mean that there's advantages. That being said, there are at least 4 key areas where quantum exhibits quadratic or even exponential advantage over digital systems. The first being simulation. Any type of simulation, whether you're doing chemical or molecular, material design, etc., weather forecasting, or financial weather forecasting. I'll give you one example. IBM, who's one of our strategic partners, they worked with a customer doing weather forecasting for anomalous events. In this case, it was hurricanes. And they were able to predict hurricane landings with accuracy 9 hours earlier than the best available supercomputers that are in use. Think of what that means in terms of lives lost and property damage that could be avoided if you had a 9-hour head start to prepare for an incoming hurricane. Very real, very tangible benefits from this technology. We're also working with a hospital in the US, a leading research hospital, and they're doing cancer research for rare childhood cancers. And again, they're seeing orders of magnitudes of improvement by using quantum for simulations in their field. Optimization. So this is finding the lowest cost solution to very complex problems. Think of the traveling salesman problem, or exaggerate that to like large-scale logistics companies like a FedEx or a UPS or something like, or any type of operation that has so many components. How do you find the lowest cost sum of all the variables in very complex equations? That's an optimization exercise. And quantum computers, particularly annealers, are the best technology there is, known technology for that. AI/ML. No doubt everyone here is aware of like why NVIDIA is the leader in this field, because they're producing graphical processing units, GPUs, which are the best tool to power the underlying mathematics of AI/ML, which is matrix multiplication, it's linear algebra. Basically, it's saying, they started making graphics cards, right? That's what it says, graphics processing units, where it says, okay, on a video game in real time, calculate how far to move an object in a given direction. So it's vector multiplication. Well, that just happens to be the fundamental underlying mathematics that's needed to power neural networks and AI. And as such, it's like a precision tool. It's like a scalpel for that particular purpose versus a Swiss Army knife like the CPU, which can do so many things, but not necessarily in a very specialized and dedicated way. But quantum does matrix multiplication at the gate level. So it's adept, it's perfectly suited to power AI/ML. And we're seeing similar results with the classical systems, with 90% less data being supplied to the quantum system. That's the kind of leap forward we're seeing. And then finally, cryptography. I'd be naive if I didn't comment on this. The race to develop a quantum computer is primarily fueled by nation states and other parties that want to learn each other's secrets. So it bears at least mentioning. Now, I'm sorry, and the reason why we say distributed quantum computing, it's like there's two ways you could build. You could build up, scale up, build a bigger and bigger and bigger quantum computer, or you could scale out by interconnecting them. Distributed quantum computers allows you to scale out. So this will accelerate the overall efficacy of all these systems. Basically, we're like the internet was of these mainframes in like the 60s, and we're starting to look to see how we can interconnect these huge machines and harness their power in a distributed manner. All right. Also, blind quantum computing. When I interface with a cloud provider to run jobs, I not only share my, I give them my algorithms and I give them my data and they do all the processing and then I get the results. Well, what if I don't want that? What if I want to preserve my algorithm as well as my data and keep that all private? With quantum, I can do that. I can use their systems to do all the calculations, but they never get to see or read any of the data or any of my algorithms. That's very appealing in many industries. Additionally, another use case is network clock synchronization. If I can more accurately communicate timing signals, say between GPS satellites, then I can even make these systems far more effective and think of like hyperlocation, but with GPS systems. And in a similar vein, distributed sensing. To say that when I interconnect sensors via a quantum network, I see a quadratic improvement in accuracy. I'll give an example. In Australia, there's a square kilometer array of deep space telescopes. They have, in one of them, it's 36 parabolic telescopes. Okay? If these were interconnected with a classical digital network, then the precision would be 1 over the square root of 36. So plus or minus 1 over 6, which is about 16.7%. Okay, so that's by margin of error. If I interconnect the same telescopes, I don't change a thing on the sensors, I leave them exactly as is, but I just change the network that interconnects their signals, I get down to plus or minus 1 over 36 accuracy. That's plus or minus 2.78%. It's a quadratic leap forward without having to touch the sensors themselves. Think about how much further into space we're able to see just by improving the network, or how much farther back into time we can see just by changing the network. And then finally, there's a more speculative use case that actually was first proposed in the 60s. That's trying again to use a special property of quantum, the no cloning principle. so that you could prevent counterfeiting of money. So while it was kicked around, it never really took off. It's gained some more recent relevance in the age of cryptocurrency, because that's very attractive then if we could prevent that kind of tampering, prevent that kind of counterfeiting by leveraging that quantum property. Okay, so those are the use cases. The biggest one, again, is distributed quantum computing. Now let's shift over and do a really, really high-level recap just to get some fundamental concepts back or refreshed on quantum mechanics so that we can, again, go through the details of how these are leveraged for quantum networking. So all physics is about the study of matter and how it interrelates to forces and energy, how matter moves through space and time. And until about 135, 36 years ago, it was thought that the smallest element or the smallest speck of matter was the atom. And then they realized, oh, there's actually a whole world within the atom. And you know what? It's not following any of the rules of the rest of matter in the universe, everything larger. It's got its own set of rules, particularly this duality of nature that these subatomic particles exhibit the tendencies of both particles. They behave like particles and net waves at the same time, which just seems completely paradoxical. Okay, but given that nature, even without fully understanding it, and there is, even the scientists today, like I say, these fundamental why they behave this way is not fully understood, but we observe it, we can mathematically model it, we can predict it, we can harness it. That's what really matters. And so here we can use these subatomic particles to express states, logical states, 0 and a 1. And we can use different types of particles. We could use electrons, we could use photons, we could use ions, and these other types of particles. These are known as qubit modalities. What mode of a qubit do you want to use to express the logical states of 1 or 0? Let's look at the most common one that's used in computing, and that's the use of electrons. So when we say, you've probably heard the term electron spin. The first thing to really understand is that the electron itself is not physically spinning, okay? They're actually too small to spin, and that's not what we're looking at. And even if they were spinning to generate a magnetic field, they would have to be spinning at faster than the speeds of light. So it's not actually spinning. But what we're looking at is a magnetic field and where it's emanating from. If it's emanating from the top and moving to the bottom, we call that a spin up. This is a relaxed state, so it represents logical value of 0. On the other hand, if it's the electrical field, as you see, is coming from the bottom and going to the top, we call that a logical state of 1. But you could have that spin happening from any of these positions. It doesn't have to be at the North Pole to the south and vice versa. It could be along any axis. And a three-dimensional object has 3 different axes: an x-axis, a y-axis, and even a z-axis. And it could be anywhere in between. And so how do we take that property to represent these logical states and ultimately these quantum states? Well, let's take a look at the quantum formula. And at this point is usually when we hear groans from the audience, because it's like nobody told me there was any math involved here, and it's in my end, it's quite early in the morning. But anyways, I think it's important because you're going to see these kind of formulas in papers or in other things, and so having at least a basic understanding of the notation and the terms will help, again, to increase the literacy of quantum and then understanding some of these points. So let's break it down. First of all, this notation is called bracket notation, and then a single subset of this is called a ket. So this is the logical state of 0, and we call this ket 0. And then this represents the logical state of 1. We call it ket 1. Now, each one of these terms has a coefficient. So a coefficient to represent the amplitude, the distance in a given direction. For ket 0, the amplitude, the coefficient is alpha, and that's the first letter of the Greek alphabet. And then we have beta to represent the coefficient or amplitude for the logical state of 1. And then the combination of these is our quantum state. It's represented by psi, okay? So how does this actually express, like, mathematically? Well, even if you're not familiar with this notation, we're going to give you at least two other ways to express the same logical concepts. So ket 0 we could express also in matrix notation. Where in matrix, again, it's distance and direction. So we're saying the top number represents the distance in direction 0, and the bottom number represents the distance in direction of 1. So here we got a full unit in the direction of 0, but absolutely no movement in the direction of 1. And then we have vice versa. If you think about this on a two-dimensional Cartesian coordinate, this is what it looks like. So we have one unit across on the x-axis representing logical state 0, and nothing, no distance in the y-axis. And then the other state is the exact opposite. And so we can represent these concepts either using the bracket notation at the top, the vectors, those square brackets in the middle, or the Cartesian planes. It doesn't matter how you represent it, it all represents the same thing. It all expresses the same concepts. Okay, so then we can simplify this equation to a vector that just says, okay, alpha over beta is how we can represent that quantum equation. And then on a graph, it's interesting to note that there's an interesting property of these amplitudes, and that is that if you square the amplitudes, that represents the probability of that value being resolved to a logical state of 0 or logical state of 1. So let's say we have 0.8 in the x direction and 0.6 in the y direction. You see that plotted out? Now, the probability means if you take a reading at that instant in time, then with a 64% chance it's going to resolve to 0, 36% chance it's going to resolve to 1. And that's how quantum works. It's all about manipulating these probabilities. Now, we recognize too that we're dealing not with two dimensions here. We're using two dimensions just to simplify this concept, but really an electron is still, even though it's a tiny object, it is a three-dimensional object. It has three planes. So for instance, it has an x plane, and that's basically a lateral from one side to another. This is a spin around the x-axis. It has a y plane, so that would be front dead center to the rear dead center, like it would be spinning around like that. And then it has also a z plane, so from the top, the North Pole to the South Pole, and then a spin like this would constitute a spin around the z-axis. That's what it looks like. Okay, now let's talk about three key properties that directly relate not only to quantum computing, but more in the context of our discussion, more relevantly, I should say, in the context of our discussion for also quantum networking. The first is superposition. So this is probably something that you'll see in the media a lot, and it's usually portrayed in a very frustrating manner. You'll say, oh, regular bits, they represent 1 or 0, but quantum bits represent 1 and 0 at the same time. And that's a logically inconsistent, it's a paradoxical statement. Yes, it's very flashy and grabs attention because it makes no sense, but at the same time, it can cause a lot of confusion. I think a better way to think of superposition is like the flip of a coin. So on a coin, you can flip it and you have two states that you can ultimately end up in, heads or tails. But when you're flipping it through the air, at the instant it's flipping through the air, what is its state at any given instant? Well, it's a probability that it's going to resolve to heads and a probability that's going to resolve to tails, and that probability is changing instant to instant to instant. And then when you catch it and take a measurement, it no longer has these probabilities of resolving to one or the other. It collapses into a single discrete state. Let me just go back. I hit it twice. So when I take the measurement, I no longer have this superposition of probabilities between one or more states. It collapses into a single discrete state. So I think that that's perhaps a more helpful way of thinking how these qubits work. They're constantly in this probability of 1 or 0. And then when you do the reading, you lose that property and it just becomes a single state with 100% unchanging probability from that point forward. Okay. Now, the other super interesting property is this spooky action at a distance. That's what Einstein called it back in 1935, where you could have these particles that could be separated by as far distances as you imagine. They could be separated by galaxies. And then as soon as one exhibited a change of state, so did the other. And it did so instantaneously. And this relationship is called entanglement. And it's interesting to note that you can entangle not just one pair of electrons, but you could actually entangle many. And the current record is 51 of these could all enter, so there's no limit, and there's no limit to the distance in between, but this special property, once it's manifest, remains in place until, again, you make a measurement and you collapse it. So what's interesting, if we want to just do a little bit of history, is that this was first analyzed by Einstein and his colleagues, Podolsky and Rosen. That's why originally it was called an EPR pair after their initials. They wrote this paper in 1935. We're coming up on 90 years, like 89 years. And so they said, oh, this is a very strange behavior. And Einstein particularly, it was difficult for him to absorb because he was the one that said nothing travels faster than light. And so how is it that there seems to be this kind of a communication, if you will, between these particles that seems to happen at faster than light speeds? But he said, no, there's something else going on. He goes, there's a local reality. Local meaning there's something near that particle, either a force or energy that's exerting influence on it. And just before we entangle it, he likened that to like putting it into a box. Just before we entangle it, it's giving it an attribute, just like these marbles. They have an attribute of color. One is blue, one is red. Just before we put them in that box, something happens that we can't measure right now because we don't have the technology, but then that fixes their properties. And then when we open the box, if I open one of these boxes far away and I see that it's a blue marble, I know automatically, no matter how far away that other box is, that there's a red marble in there. But those properties were fixed before the entanglement. Okay, that was his explanation. But then a mathematician from Northern Ireland, John Stuart Bell, came along in the 60s and says, no, that's not the right explanation. And then he presented a mathematical theorem that says, okay, Einstein can't be right and quantum theory can't be right at the same thing. Local reality, quantum theory are incompatible. And he presented a Bell inequality. And he says, no, these states are constantly changing, even after they've been put in the box, so to speak, that is, come into this entangled relationship. And it's like spinning wheels. And then whenever you make a measurement on one, that's the point where the other one, that state collapses, and you're going to get that reflective change of state. Okay, so who was right, who was wrong? Decades of scientific experimentation went on since then. And again, as Giuseppe mentioned, these are very recent accomplishments. For instance, it was just in 2022, 3.5 years ago, that the Nobel Prize in Physics was awarded to these three gentlemen who experimentally proved that actually Einstein was wrong and John Bell was right. And so quantum theory is the only explanation for the noted behavior. All right, so quantum entanglement, if you do a measurement, it breaks the entanglement. And then the final key property that we want to talk about is no cloning. Intuitively, this should make sense. If I want to copy information, what do I need to do first? I need to read the information, right? I can't make a copy of something I haven't read somehow or scanned. Well, if I can't read something in the quantum state without collapsing the state, then I can't make an accurate copy of it. And so it's like, I can't, I can just, at best, I can guess. But then the instant I try to guess, that's noted by the senders and receivers. So that cloning attempt is visible. So I cannot copy something in a quantum state. This, incidentally, can be proven mathematically. And the mathematical proof, I'm summarizing it on this slide. I just don't have the time to go through it. But basically, it takes some mathematical concepts, such as cloning. When you clone something, it basically equates to a multiplication. So you're factoring those two. So if I'm cloning particle A, I get A squared. If I'm cloning particle B, I get B squared. But the law of transformation says any transformation I apply to a part is equivalent to a transformation applied to the sum of the parts. So a transformation of A, like a cloning, then is the same as applying the same transformation to B, which is the same as applying the transformation to A plus B. Okay, so I have two different mathematical rules in place. And so if I was able to clone, then if I applied two quantum states, then I should get A squared plus B squared, but I actually get a third residual term, A squared plus B squared plus 2AB. Long story short, this is not an equality. If you want to see a good video on this point, then go to this link. But basically, this is just a mathematical proof that you can never, ever, ever clone. Okay. Now, the last thing I want to just introduce, and this is coming now from quantum compute, is the concept of these Pauli gates. Pauli gates are just doing a rotation, 180-degree rotations on a given axis. Imagine I was a little man standing on the North Pole, and then I happen to rotate 100 degrees, 180 degrees forward, and then now I'm standing on the South Pole. Well, if I start on the North Pole, which is logical state 0, and end up on the South Pole, I'm now logical state 1. This is basically a NOT operation, or a bit flip. Wherever I started with, 0 or 1, I'm going to end up with the opposite. It's like a digital equivalent of a NOT gate. Now, incidentally, if I'm a little man, again, standing on the North Pole, and I rotate around the y-axis, which again is the front dead center, so imagine me kind of rotating sideways all the way down to the South Pole, it would also be a NOT, because if I started at North Pole, that's 0, end up at the South Pole, then I'm at 1. Okay, it's a NOT, but I'm facing the other direction. If I would rotate from forward, I would be facing backward when I got there. But if I rotated from the side, I'd still be facing forward. So it's a phase. There's a phase flip as well. And then finally, if I rotate around the z-axis, this is a pure phase flip operation. So basically just rotating around different axes will give me slightly different outcomes. I'm going to come back to this. I'm not going to spend a lot of time on it, but it's just we can manipulate these qubits basically a number of ways, but we can achieve these kind of rotations. We can send, for instance, microwave pulses and then apply them at resonant frequencies and achieve these kind of rotations. Okay. Now, let's switch to quantum networking. By the way, if there are questions as we go, feel free to ask them in the chat. We'll do our best to answer them. And then if not to, we'll also follow up and make sure you get all the answers. So now, with some of these concepts in place or refreshed, let's apply them to quantum networking. Now, with quantum networking, we talked about the qubit modality of using electrons primarily for computing. That's not the only modality used, but companies like IBM and Google and many other ones are using electrons for superconducting electrons for computing. And the reason for this is because they can maintain that quantum state for extended periods of time. That's called coherence. And then when the quantum state is very fragile, when you lose it, it's called decoherence. And then also fidelity. How many times can you apply operations like these quantum gates, rotations and other operations without encountering errors? And that's an expression called fidelity. But The drawback, again, to Giuseppe's diagram at the outset, you have these supercomputers usually hanging from the ceiling, quantum computers in these 45-gallon drums. They're liquid nitrogen cooled to minus 272 Celsius. They're heat shielded, vibration shielded, EMI shielded, every type of, like everything possible to protect and preserve that very fragile quantum state. Well, can you build a network in those kind of conditions, protecting every element of the network, keeping it super cooled, keeping it fully shielded, and all of these other requirements? No. So you can't use electrons as your qubit modality. You have to use something else. The preferred and most proven and effective qubit modality for transporting quantum information are using photons. Photons do not have to be super cooled. Huge, huge benefit. So, they can operate at room temperature. They can operate over existing fibers. That's huge, because if you had to relay infrastructure for everything for achieve your communications, it would be cost prohibitive. Not only that, it can transverse into free space. So you can use these over satellites as well. So that's why we use the quantum modality of photonics for transporting qubits. Well, then how do we encode ones and zeros into photons? Well, there's 4 primary ways of doing so, and we're going to talk about them each. So one is polarization. Basically, it's the direction of vibrations. If you drop a drop of water into a pond, then the waves propagate in a horizontal plane. We call that horizontal polarization. But light isn't bound by gravity. It can, vibrate in any direction whatsoever. And as such, we can use that. I'm going to talk about each of these in a little more detail, but I just want to introduce that there are actually 4 ways that we can encode information. The next way we can encode information is a path or spatial encoding. I'm not seeing a response on the screen. Okay, it's a little bit of a lag. And then we can apply that concept further to time bin encoding and finally frequency bin encoding. There seems to be a little bit of a lag, but we're going to do our best to adapt to that delay. Okay, let's look at each one of these in turn so that we understand the different encoding methods. So as I mentioned, let's start with polarization encoding. Now, usually these are done on the horizontal and vertical plane, but it could also be done diagonally. I'll show you an example of that next. But again, think about it. If light is vibrating and transmitting on that flat horizontal plane, we call that the relaxed state, so representing logical 0. And then if it's fully vertical, then this is the excited state, and then that represents logical value of 1. Typically, so then here's our quantum equation showing the coefficients of that superposition of states. And then we can do this on a vertical perpendicular axis, or sometimes it's also done on a diagonal axis. So where one axis is 45 degrees, the other one is 135 degrees, or minus 45, however you want to express that. And then this is how we express 0 and 1, as well as the superposition of states anywhere in between. It's really, really good for free space. Okay, this is important to recognize that not every method is ideally suited for every media. It's very good for free space, but it's not so great in fiber optic cables because the glass twists and then it can interfere with that polarization. So another method is to say, okay, what path am I taking? And for this, we use a device called the beam splitter. And sometimes you may have seen images of a beam splitter, like the one that's about to appear, and here it comes, that basically says, okay, there's an angled glass, and either it will go straight through 50% of the time, or it will be reflected in a different direction. And then, so basically there's 2 ways, 1 way into the box, 2 ways out. And so we have one path versus another. once the beam comes in, and then we just say, okay, which path did it take? And it's a superposition, and then we use that to encode the states. Now, a slight twist on that encoding method is to use a time bin. And bin here, basically think of it like a trash bin or like a recycle bin. You have multiple of these containers you can place an object in. Okay, so that's what the context we're using bin here. And basically, it's the same as path encoding, except that we are looking at how long it takes to get to a direct detector. And there'll be two different paths. There'll be a short path, and then there's going to be a long path. And so when the light comes in, again, we're focused about timing here. And we can say, okay, when the light comes in, if it takes a short path, it's going to arrive early at the detector. If it takes a long path, it's going to arrive late. And depending on those arrival times, those synchronized arrival times, we can then achieve that superposition using time bin encoding. Now this one, in fact, is much more suitable to fiber optics because then even if the cables are bent or there's temperature changes, it doesn't interfere with it. And finally, light has different frequencies. This is like colors. This is how we determine and detect colors. We could say, okay, well, what color is this light? And then we could use different frequencies of light. And that way we could achieve, again, a distinction between quantum states. Incidentally, this is similar then to what we use for dense wave division multiplexing, using different types of colors of light to really pack a lot of information into single optical cables. So we've already used this in digital circuits, and then we could apply it even into quantum. Okay, but then we also talked about entangling. How do we entangle qubits at the quantum layer? Well, there's various methods. One of the simplest and easiest to understand is what's called spontaneous parametric down conversion. It's a huge, big, fancy name, but basically what it amounts to is you take a laser and you generate one high-energy light photon and you shoot it through a crystal. It's a nonlinear crystal, and then that just splits it into two lower energy photons that enter this special relationship of being entangled. And you can do this at room temperature. Here's what it looks like on an optical testbed. Okay, so then how do we use all this for communications? Well, let's think of how we currently communicate via optics. We send a blast of photons, a lot of photons at once. And if you look carefully, what you'll see in the animation is that not all the photons make it. I'm going to run it again. You see that some of these photons disappear en route, and that's just a function of noise and attenuation. But if we're dealing with single photons, and if we have a single photon that's encoded with a qubit state, quantum state, and we send that and we lose it, now we've lost all our information. And this is then very difficult to manage because we're dealing with something so tiny and so fragile. And if we lose it, we're done. So then how do we get by this? Well, how do we solve this problem in classical networks? Because this problem exists already. And so this attenuation, it basically says that the fidelity of your information transfer decays exponentially with distance. That's huge. So the longer that fiber optic, the more and more and more of this loss you're going to experience. Well, they say, well, how do we deal with it in regular classical networks? We just amplify the signal. We do repeaters. So why don't we do that with quantum? Well, it's not that simple. Because we can't read and then recreate that information. If I take a bit, I take it in, I say, oh, is this bit 0 or 1? Okay, I'm going to generate a new bit that's 0 or 1, and then pump up the amplitude of it and then recreate it. But I can't do that for quantum. I have to preserve that quantum state. So this is not an option available to me. So then I need a different way of doing things. And this brings us to teleportation. Yes, it's a real thing. It's not like it's deployed, described in like movies or TV shows like Star Trek where people are moving around. Maybe one day, I don't know, I doubt it. But anyways, let's apply it to quantum communication. How does this work? We have a sender, Bob and Alice, and Bob and Alice are actually interconnected by a classical channel. Let's say it's a fiber optic cable. And so the first thing I have to do is I have a quantum bit that Alice has, and she wants to transfer that and preserve its quantum state, get it over to Bob. So the first thing I do is I establish a carrier, if you will. And this carrier consists of a separate entangled pair. And so these two new photons are entangled and enter this relationship. They're carrying no information at this time. They're just a random, whatever state they were in, they now share that state. And Alice sends one of these photons over that classical channel to Bob. Okay, this is preparation. Okay, this is establishing now, if you will, a quantum channel for communication. Now, Alice performs a second entanglement that says, okay, she's going to take the bit that the quantum bit she wants to convey, and she entangles it with qubit A. The instant she does that, the shared state is reflected over at Bob's. But Bob doesn't get a clean state of just qubit A. He gets noise and signal because it's the state of qubit A and Q at the same time that are now reflected in photon B. Okay, so there's signal and noise. And that noise is, we don't know, it's random. And it could be at one of four states, four Bell states, at that instant of entanglement. What we do, we don't want to make a measurement because we'll lose our quantum information. We don't want to make a measurement on Q, but we can make a measurement on A, an indirect measurement that's called a Bell state measurement. That'll give us an indication of what its state was at the moment of entanglement. So basically, we need to know how to remove that noise because right now B contains signal and noise. So we make that measurement, three things happen all at the same time. We break the entangled relationship, we collapse the superposition only of qubit A, because we measured qubit A. We did not measure qubit Q. And then this is going to give us one of four Bell states, one of four maximally entangled states. And then I take that state, and because there's only four, I could represent each of those states by just two classical bits, 0 and 1. For example, in this case, and then I have to send that information again over my classical channel to Bob. So now Bob knows what to do to untangle, to get rid of the noise that's in B. And so he's going to remove the noise. Either he does nothing, he may not have to do a single thing, or he has to apply a mirror reflection, rotation around the x-axis, the y-axis, or the z-axis. And this will all be determined by the classical information that Alice has sent him. And then once he does that, he's recovered his quantum information and it's pure. The noise has been removed from the signal and he's never read that qubit, so it's preserved in that quantum state. That's tricky to understand. If you want to, go back on it a few times, but basically that's the key steps for quantum teleportation. Now, we also introduced the term of entanglement switching. What do we mean by that? In the previous diagrams, just for simplicity, we had all the entanglements set up at the sender and then sent to the receiver at Alice's end, and then she sent one of those photons to Bob. But really, practically, it would be more efficient to have this done in an intermediate network device, like a quantum switch. Think of this as a top-of-rack switch that's directly connected to both endpoints. And so I generate that entangled pair at the quantum switch. I send out the photons from the switch to the endpoints, and then now they can communicate over that quantum channel. But what if I'm not directly connected to each of the endpoints? Well, now I have to do a more complex operation. This is called entanglement swapping. So let's build it out again. I have my switches, and then these switches, they extend their entangled pairs to, as many devices as it takes until I have a whole overall link, and then I do what's called entanglement swapping. And now I have a chain, an end-to-end chain of entanglement. Remember, I can entangle more than just a pair of photons. Currently, I think the world record is 51 of these can be entangled, or they've achieved that. There's no limit, but just practically they've been able to achieve that. So I can entangle more and more of these together until I form the necessary chain that gets me all the way from my sender to my receiver, regardless of how many intermediate devices there are. So then think about going beyond switching, how this would work for networking. Well, again, if I simplify the presentation and say, instead of starting with intermediate devices, let's say I start from sender to receiver. What are all the steps I have to involve? I'd have to do these primary link entanglements. I'd have to achieve all my entanglement swapping on all my intermediate devices. And then that will achieve that end-to-end entanglement chain. Oh, it's a little bit lagging, but anyways, then once I have that end-to-end entanglement chain, I can transfer the information. If there's a break or if something happens, then I have to reestablish that end-to-end entanglement and do all these steps again. And then there's all this repetition of the processes involved, and then I can recover and resume. It's very similar. If you want an analogy and you've been in networking for a long time, it's very similar to ATM SVCs, that is asynchronous transfer mode switch virtual circuits. So what goes around sometimes comes around in networking. Anyways, then this is now all led up to, with all this foundation having been laid, hopefully then this helps understand and maybe increase the appreciation of what Cisco has been doing in quantum. So some of the key challenges in quantum is obviously creating larger and larger quantum computers. This is scaling up. How many qubits are going to go into a single computer? And that just keeps going up. Achieving longer coherence and all of these other elements. But the area of focus that Cisco is applying themselves on, we're playing to our strength. We're 40 years plus a networking leader. And now we're bringing all that expertise in networking, in photonics, in communications and protocols and security to the field of quantum. And so this is where our area of focus is. And the overall steps to building this quantum internet, well, it all starts with research and modeling, mathematical modeling. So we have a team of quantum scientists that are part of our OutShift department and leading this type of quantum research. We also do a lot of simulation and emulation. And then finally, we build things out that are real, like on optical test beds, and even deliver new hardware solutions and software solutions to realize this. Let me share some of them. So for example, we were one of the leaders to define how we could build a classical and quantum internet. We saw from the diagrams that to communicate, you had to have not just quantum exchange, but you had to have some information exchange on classical channels. Alice had to send the Bell state measurement to Bob. Alice had to send the entangled photons to Bob to begin the whole process. So we need both. There's never going to be one or the other. It's always going to be a hybrid. Just like quantum computers are not pure quantum, they're hybrid, digital and quantum computers. It's the same for the networks. And then we keep publishing these papers, 8, sometimes 10 a year. For instance, just very recently published, this was from March of this year. And this was a breakthrough, basically showcasing how we actually did high-speed entanglement swapping 500 times a second over existing fibers in New York City on very significant different distances, 17.6 kilometers. And we did it without a shared clock. Like usually these type of experiments, just for context, are done in labs in highly controlled environments and with very expensive equipment. But here we actually took it to real world scenarios and used existing infrastructure. And we were able to solve a lot of problems and challenges by our new approach. And again, all ultimately proving that these are all practically possible. And we're already starting to achieve quantum networking over our existing infrastructure. Beyond research, we also are developing hard simulation and emulation solutions. So perhaps some of you might be familiar with IBM's, QNet labs, where you can actually go and you can program quantum computers. It's actually pretty cool. And then you can run your algorithms on their quantum computers and see all the results. Well, it's very similar. We can do the same for networking. We can use these simulators and emulators so you can design your quantum networks. You can play with parameters such as loss and noise and attenuation and see the effects of topologies, et cetera, and then you can then optimize before you even go to an optical test bed to build it. We are also have developed software solutions, recognizing that, hey, if I'm going to split the execution of a quantum algorithm over multiple distributed quantum computers, there's a lot of logic that has to take place for timing, for synchronization, for error correction, for scheduling, and all of these problems. And we've produced an industry-leading solution for this that actually enables that. And then going beyond software to look at what we're doing in hardware. One of the first hardware elements we produced was a quantum random number generator, because any random number generator you need, and we need this for simulations, we need it for cryptography, we need it for other purposes, they're not actually fully random, they're pseudo-random. And I'm sorry, I'm losing all the sharing. Can you guys hear me, or can somebody confirm if it's still being shared?
I can still hear you.
Still hear you, but
yeah, I lost
the slides are
the
gone.
slides.
Okay, that's very strange.
Yeah, now the slides are back.
Okay, that's very bizarre. Okay. Another piece of hardware then we developed, this is last year, was an entanglement source, that quantum teleportation chip. And basically, again, key elements, operating at room temperature, integrating with existing fiber, 1 million of these pairs generated per channel with a rate up to 200 million per second, and extremely low power requirements. So this was a huge breakthrough from last year. And then just a couple months ago, I've come full circle to my opening slide. And yes, at the end of April, we announced our universal quantum switch. So now when you read about it and you say, oh, multimodal, oh, okay, I know about the various encoding modes for quantum circuit. I can encode that information using polarization or time bin or frequency bin. I know what now they're talking about and what's new, because basically we make it any to any, and it doesn't matter how it's encoded. As it comes to the switch, we're going to interoperate with it, just like we did with our original switching and routing equipment years ago, recognizing that we don't want to dictate, okay, what's going to be the predominant forms of qubit modalities and qubit encoding. We're going to support them all. We're going to be flexible. We have that leading fidelity for entanglement and teleportation. Now you know how teleportation works, etc. Also entanglement switching, which is different, and subset of entanglement swapping. And we can achieve that at very high speeds. So hopefully all these slides I started with at the beginning, but hopefully about an hour later, it makes more sense and you're more familiar with the terminology here, and then ultimately hoping that there's an appreciation like, hey, using real world infrastructure, what were all the challenges that went into that? Or energy efficiency, or operating at room temperature, and all of these engineering challenges, what it took to achieve. Hopefully our discussion it added some context and appreciation there. Okay, so we've come to the end of our discussion. Let's see if how those 5 questions, how they have gone. Let's recap what they were again. Why build quantum networks? What are some of the special properties of qubits that we discussed? Can you transmit information faster than light? And I want you to focus on the word information. And will quantum networks replace classical networks? And what's Cisco doing? Let's take them one at a time. Why build quantum networks? Feel free to use the chat or however means you want to submit your answers. I'm not seeing anything, but anyway, some of the use cases. The original use case for quantum networks with quantum key distribution, we see that in various rings, particularly in banking centers around the world, like in Geneva, in London, Singapore. China's got over a 1,500 kilometer QKD network. That was the original use case, but then we see all these other ones that we talked about. And the big one, the most predominant one that we are building for, and it's going to be the ground changing one, is distributed quantum computing. To scale out, not scale up. Other companies are building bigger and bigger quantum computers. We're going to be scaling out these quantum computers by interconnecting them in quantum networks. Okay, what are some of the special properties of qubits? Well, we talked about a few of them. We talked about superposition. Remember the flipping coin? It's instantaneously has a probability of 1 and 0 at the same time. Entanglement, excellent, Kristen, thank you. Entanglement's a huge one, and we leverage that extensively in quantum networking. And then finally, no cloning. Very nice, Wissam. Excellent. I love it. I love it. It's great to see the feedback coming in. And that's a unique property, particularly for security purposes. It also limits our options a little bit. It ties our hands when it comes to communication. But anyways, it's a double-edged sword. Okay, 3, can you transmit information faster than light with quantum teleportation? So think about this, and I again invite you to focus on the word information. So remember what we had to do to transmit the teleportation. The first thing we had to do was send a photon from Alice over to Bob. It had to go over a classical channel. Then we entangled, and then we did a measurement, and we had to send the result of that measurement over to Bob so that Bob could remove the noise from the signal without reading or affecting that original qubit. He would have to do a rotation. Well, do nothing or do a rotation, one of 3 axis rotations. So does it allow for information transfer? No, because we basically sent a random state, a random 1 or a 0 from Alice to Bob. That part was done faster than light, but it's not information. It's not information until we can make that correction. And we had to establish a channel to begin with. We had to then also send those 2 bits. So no, we're not transmitting information faster than light. That's important to understand and then appreciate. And then you can myth bust. Will quantum networks replace classical networks? Well, no. Great. Excellent, Kristen. And that's again following our discussion to say, look, we need to send a bit over a classical channel, at least one, to establish the communication, the teleportation entangled pair. And we have to send the result of this Bell state measurement. So for every qubit we're transmitting at least 3 over a classical network. There is a mathematical dependency. You are never going to have a pure quantum network. It will be always hybrid, just like computers. Quantum computers are hybrids. What's Cisco researching and developing in quantum? Here's my last slide. Basically, we're doing a lot of extending pioneering research. We modeled the quantum internet. We're proving that it's practically realizable. This is just like a couple months old, this test. And we're building software for simulations, emulations, digital twins. We're building hardwares like our quantum random number generator, our entanglement chip, and also our universal quantum switch. Again, hot off the press, just a few weeks old.